My name's Evie and I'm a Year 13 student. Sorry, it's taking a bit to press next. Okay, so there's just a few rules and safeguarding before we start. We need to set a few clear boundaries in place. We do not provide one-to-one support. Microphones should remain muted and cameras should be turned off, particularly if you're under 18. This session is being recorded. If you are under 18, please let a parent or guardian know that you're attending this session. By attending this session, you're agreeing to the MedDent Network's safeguarding guidelines. So, here's the AQA specification for halogenoalkanes. It's broken up into 3 sections: nucleophilic substitution, elimination, and ozone depletion. So, starting with nucleophilic substitution, we need to know that halogenoalkanes contain polar bonds, which, if we remember from previous sessions, are bonds where you have 2 opposing forces, so the positive and negative side, causing an atom to have a dipole. Halogenoalkanes undergo substitution reactions with the nucleophiles OH-, CN- and NH3. So that's ammonia, hydroxide ions and cyanide ions. Students will be able to outline the nucleophilic substitution mechanisms of these reactions, which is key in remembering the different reagents and how it all works, as well as explain why the carbon-halogen bond enthalpy influences the rate of reaction. Bond enthalpy is just the energy taken to break the bonds of a molecule, and the rate of reaction is just how quick the reaction happens. So for elimination, we should know that the concurrent substitution and elimination reactions of a halogenoalkane, e.g. to bromopropane with potassium hydroxide. Students should be able to explain the role of the reagent as both a nucleophile and a base. And a base is just a proton acceptor, so that means accepting a H+ ion, and a nucleophile is something that's attracted to a positive charge, and it itself will have a lone pair of electrons that it's able to donate to it. And then we need to outline the mechanisms of these reactions. For ozone depletion, we need to know that ozone, which is O3, excuse my handwriting, formed naturally in the upper atmosphere, is beneficial because it absorbs ultraviolet radiation. Chlorine atoms are formed in the upper atmosphere when ultraviolet radiation causes carbon-chlorine bonds in chlorofluorocarbons, it's a mouthful, to break. Chlorine atoms catalyse the decomposition of ozone and contribute to the hole in the ozone layer. We need to appreciate that results of research by different groups in the scientific community provided evidence for legislation to ban the use of CFCs as solvents and refrigerants. Chemists have now developed alternative chlorine-free compounds. To put this into practice, students should be able to use equations, such as the following, this one below, to explain how chlorine atoms catalyse decomposition of the ozone. So here we've got a chlorine-free radical, which I'll explain this later. Chlorine-free radical at ozone creates another radical, an oxygen, and then again we've got another radical here, plus ozone, creates another molecule of oxygen. So we're breaking the ozone down into oxygen, which we don't want to happen. So, what are halogenoalkanes? Halogenoalkanes are a molecule where a halogen, a molecule of group 7, takes the place of a hydrogen atom in an alkane. Halogens are more reactive than alkanes, and the general formula is CN2N plus 1 X, and this X just stands for a halogen, maybe such as bromide, but we could also have chlorine as well. And when we name these molecules, remember in the nomenclature from earlier topics, we use these prefixes: bromo, chloro, fluoro and iodo. And the way that we put these into practice is, say, if we had a molecule that looked like this, with a bromine atom and all these hydrogens here, it's molecule of ethane with bromide added onto it, so we would name it 1-bromomethane, which it makes more sense when you have a longer molecule such as propane, and then you can number where exactly this bromine is on the molecule. The reactivity of halogenoalkanes. So if we remember electronegativity, it's the ability of an atom to attract a pair of electrons, keyword pair here, because especially in the AQA mark scheme they're very specific about saying pair of electrons in a covalent bond. So the higher the electronegativity of an alkane and the polarity of the carbon-halogen bond, remember this could be something like bromide to make it clearer, the greater the dipole formed. So in this table here, we've got lots of halogen molecules, and each have different abilities, strengths of electronegativity. So here, fluorine is the strongest one, and just to define electronegativity even clearer, it has to have a electronegativity of greater or equal to 0.5 to be classed as electronegative. So the chlorine-fluorine bond is the most electronegative, which means we have a bigger dipole here. So we have a partially positive carbon, partially negative fluorine, because the fluorine is taking all of the electrons in the bond and taking this electron density over to its side, causing that polar bond. So as the polarity of the bond decreases and its electronegativity decreases, we have a weaker bond enthalpy or bond energy, which means they're essentially they get easier and easier to break the weaker the bond, so it takes less thermal energy to break. Halogenoalkanes with a greater dipole are less reactive due to the strong intermolecular forces that take more energy to overcome, which I essentially just outlined, but it just means that the reason this is decreasing is because we need less energy to overcome the decreased polarity. So to really put this into practice, when we explore the reactivity of halogenoalkanes, we can do a simple test tube reaction just to visualise it. So by adding aqueous acidified nitrate solution to a halogenoalkane, we can get a hydrolysis reaction. So we've got these 3 test tubes here, each with an equal amount of acidified nitrate solution and an equal amount of a halogenoalkane. And how quickly this forms a precipitate shows us how quick the molecule can react. So the carbon-halogen bond breaks and the halogen ion is released into solution. So this should be up here really, but so let's say the bromide ion is released into the solution, and then this molecule is formed, AgX, which is for the halogen, AgBr perhaps, precipitate is formed. So the rate precipitate is formed correlates the reactivity of the halogenoalkanes, and as we've seen before, reactivity decreases down the group in the periodic table from fluorine to iodine, because these bonds are getting easier and easier to break. So iodobutane creates a yellow precipitate, and that's the first one to form, which means it's the most reactive, it's got the weakest bond, the lowest, which is the least polar and the most electronegative. Bromobutane is the second to form, that's a cream precipitate, and chlorobutane forms the last, and that has a white precipitate. So now moving on to the mechanisms. There's 2 mechanisms which you saw in the spec earlier, nucleophilic substitution as well as elimination. So in nucleophilic substitution, a nucleophile which donates a pair of electrons to form a covalent bond with an electron deficient atom, which will make more sense when we put it into practice, but it's drawn to the positive charge. So on a chlorine, positive is drawn. So we have a halogen ion, bromine. We always go from negative to positive, and it's drawn to this positive ion here, and it forms a covalent bond by donating its electrons. So a halogen is substituted for another atom or group of atoms. When halogens undergo this type of reaction, the products are alcohols, amines and nitriles, and this just depends on the type of reagents we use. So for alcohols, the nucleophile would be OH minus. For amines would be NH3, and the reason this one isn't an ion, but the reason it's reactive is because we've got these two lone pairs here. It's very important to always remember the lone pairs. And nitriles, so those are the C triple bonded N, and that's got two lone pairs here as well, and the negative ion. And it looks a bit funny written this way, but we need to remember that the pair of electrons always goes on the right atom. So on this one you have to have it next to the O, on this one next to the N, and this one next to the carbon, because that's where it sits on the molecule, and we need to represent it accurately. Also where the negative charge should go. So we talked about this a bit easier. So the polar bond creates these two dipoles, and we have all the electron density here and less here, which makes it slightly positive. So these nucleophiles are drawn to this molecule here, due to carbon having a lower electronegativity and the halogen having a higher electronegativity. So actually doing nucleophilic substitution, it's important with this one not to get mixed up with elimination with the reagents. So we need to remember it's a warm aqueous, not ethanolic, aqueous solution of sodium hydroxide, which you might also be seen written as NaOH. Yeah, so we've got the nucleophile here, which is the OH minus, the hydroxide ion, and as you remember, it's being drawn to this positive charge. It's always negative to positive. So it's being drawn to this positive charge, and we draw this with a curly arrow. Always has to be curly. This is very specific, especially in OTR mark schemes, I believe. It's drawn to this partially positive charge caused by the dipole with this atom. And then this bond now has too many bonded to it. It's got 5 bonds, and we only have 4 bonds on a carbon. So this bond here, because this has a higher electron density, all of the electrons from the bond come onto this atom here due to state symbols. In some questions they'll explicitly tell you to state symbols, but I double check with your example because don't completely know the answer to that one. It's better to state symbols rather than not to, especially if you're forming an equation. But when you're drawing out the mechanism like this as a displayed formula, then no, you don't need to. So it takes all the electrons, which is called heterolytic fission, which I'll talk about more later on in the slide, but which means it's unevenly taking all of the atoms. So then the next step is we have the full molecule, and this just makes it easier to visualise, and we can also name it after this. Excuse the poor drawing. So we swapped the bromine with this OH minus to create an alcohol, and what happens to this? We can just leave it as Br minus, or sometimes it gets bonded to to a hydrogen as well, creating HBr, but it's okay just to leave it as the hydrogen bromide. Just remember the lone pair is still here, and this would be it would be ethanol. That would be ethanol. Yeah, this would be ethanol, because it's just the, remember when we name acids, just the ol on the end, and then the 2 here, which is ethane. So it just creates ethanol. And then nucleophilic substitution with NH3. The conditions for this are ethanolic solution of excess ammonia, and that's important because, as you'll see in later topics, this is a very important condition, so that we create the primary amine that we want. We don't want any other types of amines, we just want this primary one here, and we heat it under pressure. So again, we have got the partial positive on the carbon and partially negative on the bromine, because it takes all the electrons in the bond over to that side. Don't forget the negative here. So this one comes down and attacks the carbon. Ideally we'd like this arrow a bit closer to the carbon, perhaps here. It's just for clarity and difficulty on the PC, that I don't want to get in the way of the partial positive. So this comes and attacks it again. This bond, these electrons then move to the bromine again, and we create a primary amine. But the difference with this one is that we have a positive on this amine, because we have 4 bonds to it, which it doesn't like, so we need to remove one of them. So we just do this by reacting it with just taking this bond here and putting it on like that. So this hydrogen gives its bond away back to the nitrogen ion, so that it's no longer, this might come, I'll come down here, so that it's no longer a pro-lead bond, because it's unstable when it has a positive ion on it like this, and we need it to be stable. So it's just primary amine, and the name of this amine is ethylamine, because we use the prefix of the hydrocarbon that we have here, which is ethane, and then amine, so ethylamine. And then the same mechanism again, unfortunately, nucleophilic substitution with Cn-, 2.C. So for this one we need ethanolic solution of potassium cyanide, which you could also write as KCN in ethanol, heated under reflux. So again, not forgetting the negative charge or the lone pair here. We don't need to draw the, not for AQA at least, we don't need to draw the partially positive or partially negative here. It just makes more sense to visualise it in your head and understand what's going on. So I won't draw them for this one, but you won't be penalised points in the exam if you do draw them on. So it's attracted to the partially positive carbon, and then this bond comes off into the bromide. It doesn't matter which way you draw in this arrow, I just drew it here so that it didn't intersect with that one. And then when you name this one, we need to remember that we've added on another carbon, so we include that within the name. So this was a 3-carbon chain, which means it's a prop. So it should be propane nitrile. because we've got this nitrile group here. Elimination reactions. In elimination reactions, a hydrogen atom and a halogen is eliminated during the reaction. The products formed are an alkene as well as a hydrogen halide. So that just looks something like HBr, or you could have HCl. So just a hydrogen attached to a halogen. Halogenoalkanes are heated with ethanolic sodium hydroxide. So that's why it's very important to distinguish between the nucleophilic substitution step, because if we can have aqueous sodium hydroxide or we can have ethanolic, and ethanolic creates this elimination and aqueous creates nucleophilic substitution, so it's important to be able to distinguish between each one. I think there's just somebody, so that's why we need to remember ethanolic sodium hydroxide. The carbon-halogen bond breaks heterolytically, which I mentioned earlier, is giving both electrons to the more electronegative atom, rather than evenly giving it to both. So in, as we had before, the C, I'll just rub that out, that's a bit unclear. As before, we had this CBr bond. As this one's more electronegative, and this one's less so, it takes all of the electrons to itself, leaving this one with none of the ones from that bond. So it's unevenly breaking again. So the mechanism itself, this one I like to visualise as a staircase, and you'll see what I mean more in a minute. This can happen either side of the atom, so we could have it happen here, or we could have it happen here. And it just, when we're doing EZ isomerism and talking about alkanes and how they can move around, how they can't move around the bond, and how we have to take into account the geometry of it, that's when this comes into play and we have two separate isomers, stereoisomers of the molecule. So here I'm going to attack this hydrogen, and then this bond here, right next to, underneath the hydrogen that you've just attacked, comes down and moves its electrons onto this bond, and this is where we form double bond, the pi bond. Because this, and this all happens in one step when you show it on the mechanism, because this now has too many bonds, it has 5 because we've got the double here, then this is when heterolytic bond breakage happens, because this takes all of the electrons for itself, so that carbon's no longer has got too many attached, no longer positively charged. So the product of this, so it might look quite complicated right now, we've got this double bond here which we've just formed, and this hydrogen has been taken away, because although the arrow is going this way, we always have to have negative to positive. This hydrogen has still been taken with this OH minus, this hydroxide ion, to form a water molecule. So this is why this hydrogen's no longer here. It's only got 1 on it. The bromide ion has also been removed. So although it looks a bit, we've got the double bond here, 4 bonds on each one, plus H2O, because we formed the hydroxyl ion with the hydrogen, add Br. It's important just to remember these products, because oftentimes they will ask you for it, and it is part of the mechanism itself. So remember, that's heated with ethanolic sodium hydroxide. So sodium hydroxide dissolved in ethanol. Onto chlorofluorocarbons. Halogenoalkanes that contain chlorine and fluorine but no hydrogen are called chlorofluorocarbons. So I think this is easier just to visualise. We've got the carbon in the bond in the middle here, and then we've all the bonds coming off it are just either fluorine or chlorine, which makes for, as you can imagine, a very reactive molecule. They were used as solvents in refrigerators, and when they break, CFCs rise up to the ozone layer, which can lead to ozone depletion, which is bad because ozone absorbs UV light in the atmosphere. Now, UV light, we need to have that absorbed because that can lead to things like cancer within the population, or it's a very important thing, this ozone layer that we have, for life on Earth itself. If life on Earth probably wouldn't have developed without this ozone layer, because we would have had too many cancers and DNA mutations because of all this ozone coming in. So having CFCs catalyse the breakdown of this ozone is a very bad thing. But chemists have luckily now developed hydrofluorocarbons, and we use these in refrigerators instead because they were very useful whilst we had them, and that was the only effect. We could also add them in aerosols and things as well. But after this research, we've had to change them to hydrofluorocarbons, which, as remember, fluorine has a more electronegative bond, which means it has a higher bond enthalpy, so it's less likely to be broken down by UV light and catalyse this reaction. So the depletion of ozone. UV light breaks the CCl bond in CFCs. So if we draw the atom like this, see, we'll just have 3 fluorines and 1 chlorine on this one, and then UV light causes it to be break down into these 2 free radicals, CF3, because we've lost this one. Look, it's been broken down, it's been taken away, so we've got extra space here on the carbon where there shouldn't be, plus a chlorine free radical. And I'll show you how this catalyses the breakdown of the ozone itself. And if you remember from when we started, ozone is just O3. The overall reaction, before we start that, is 2O2 to 3O2. 2O3 to 3O2. So that's 2 molecules of ozone breaks down into 3 molecules of oxygen. That's the balanced equation, which creates this hole in the ozone layer, as we saw just before COVID, causing more UV light to come through, which could cause more cancers and things like that. So it's not very good, and we don't want this to happen. The steps that happen after the chlorine has been radicalised. So you've got the chlorine free radical here, plus a molecule. Oh, this is a bit far off again. Plus a molecule of ozone, O3. And then these react to create chlorine and oxygen bonded together, chlorate free radical, as well as oxygen. So we have this is the intermediate step here, the ClO plus oxygen, and this then goes on to catalyse more in the next equation, but we've still got oxygen as a byproduct here, which shows it already breaks down into a lot, because we already have some and it's not even the end of the reaction. So the ClO radical then bonds to more ozone in the ozone layer and creates 2 molecules of oxygen, so that we've got 3 overall here now, as well as another chlorine radical. So the cycle just goes on and it's a bit endless, which is why we've had to introduce these new measures and create hydrofluorocarbons so that this doesn't happen, because once these chlorine free radicals are in the atmosphere, once they've been broken down by UV, there's not much we can do to then stop them breaking it down and catalysing. And luckily, after COVID, when people stopped going out and we stopped using these aerosols and solvents in refrigerators, the ozone layer healed a little bit, but it's still very important and a big scientific breakthrough to understand this process. And in exam questions, they often expect you to give either this overall formula, but definitely this one comes up a lot, the whole propagation and breakdown of it itself and free radical substitution. So it's definitely something you should know and remember and keep in your flashcards.